Hello to my friends joining us via recording. Today we are wrapping up lesson number 7 and moving into lesson number 8. We just finished up oh yeah, Audrey's mentioning the pretty screen. Yeah, I'm gonna go ahead and leave it on this today. Thank you for the reminder though. We just finished up the lab midterm exam. So to help us stop and think it through or pause for a moment halfway through the semester, we chatted with our neighbors about what we did that helped us on the exam and what we did that didn't help us. So I'm going to ask my friends that are here in class to help me out in the chat. Let's start with, let's actually start a little bit backwards. I want to start with things that you did when you were preparing for the exam that you felt like weren't very helpful, or things that weren't as helpful as you expected them to be. What were some of those things that either didn't help or they weren't as helpful as you thought they would be? Okay, so Kaylin's mentioning not taking any breaks. Yeah, I think that is a very valid thing. It is really true. I heard Kaylin's group talking about this, how you do learn more when you pause for a moment, give yourself a breath, get up, go get a snack, take a drink, reward yourself with a little bit of phone time, right? Let's have a moment of being real with Dr. Aulis. When I'm going through and grading current events, I will legit tell myself, if I grade 10 of these assignments, I get to play a game on my phone. And then I got to grade 10 more, and then I get to play another game on my phone. So you motivate yourself, right, with little breaks to make it through stuff. So yeah, taking those breaks, definitely important. Yeah, Elapena mentions worrying, not super helpful. Absolutely, worrying or stressing. I could see that not being very helpful. Oh yeah, so along that worrying line, right? So technology worrying. Yeah, Kira mentioned that she had some issues with her internet connection. So I'm glad to hear that you didn't lose your internet during the exam. That is very scary. I feel like after snowpocalypse too, we're all like very aware of just how unstable things are, right? I feel way less confident in my internet and my power than I used to before the snowstorm happened. Yeah, the infrastructure is not what you think it is, right? So I'm glad that it didn't go out on you though. Okay, yeah, and Audrey's got a really good point too about flashcards. So not making flashcards as we learned stuff. I'll say that. So this is actually a great point to make right now as we're getting ready to move into the next half of the lab semester. It would be a very good idea to make your flashcards as you go, just so that you have something to constantly be reviewing throughout the semester. There's going to be way too much stuff to be making flashcards for the week or two right before the exam. So if you can make your time to start doing them now, it's a good study technique. Definitely make those flashcards as we go for sure. Yeah, so on the worrying train, freaking out too, yeah, that's not going to help. So yeah, the other thing that I'll mention that usually students tell me too is procrastinating. So that kind of, I guess, goes along with when we make those flashcards, right? So waiting till the last minute, or waiting a little bit longer than we should to start reviewing that stuff that we really don't like. So if we can start making our flashcards as we go, if we can keep studying as we go, I think that will definitely help with that. Yeah, Kaylin mentions having a meltdown. I bet that didn't help either. So when that worrying spills over, right? All right, we talked about some of the things that we did in preparing that weren't super helpful. Let's switch over to some of the things that you did that were really helpful for you. What were some of the ways that you prepared for the exam that did help you? What were some of the good things that we did? Yeah, so those review assignments, absolutely. The review assignments, I'm glad to hear they were helpful. Doing them repeatedly, absolutely. We could add to our list too, doing them early, right? Trying to do them ahead of time would be helpful. Yeah, and Kara mentions doing the review assignments without notes. Absolutely. Especially when we get closer and closer, and this is true for lecture and lab. The closer we get to our exams, the more you really should be trying to do those assignments without notes. Because if you're relying on your notes to get your 80s and your 90s and your 100s, as you know, we don't get those on the exam, and that makes it a lot harder. So definitely we're looking toward, I know we don't like to think about this already because we just went through our lab exam, but the next lecture exam is coming up fast. So we need to start thinking about starting those review assignments for the next lecture exam too. So review assignments, helpful for us. I know somebody else had mentioned their flashcards. Those can always be super helpful if we make them early enough. Yeah, so reviewing all of the content with a highlighter, finding the most important stuff, content with a highlighter. Yeah, so there was a question about when that next exam is. Yeah, Kaylin is correct that as soon as we get back from spring break, Monday, Tuesday after spring break is when that exam is going to be. So we still technically, since we have spring break, have a lot of time if you think about it in that regard. But in terms of class weeks when we're doing stuff, it's coming up fast. So we still have a little bit of time. Any other things we want to add to our list for what we did that was helpful? The review assignments, the flashcards. Usually students also tell me watching class videos or attending the live sessions. I get that a lot. Attending sessions live, that seems to help. Yeah, asking about review sessions for the exam. So we're going to do one this Friday. And then, yes, we will do one Monday right when we get back. So we've got a couple of review sessions for that lecture exam coming up. Those hopefully helped you out when you were preparing for the lab exam. I think they'll help you for the lecture exam too. One other thing, I think that people have said this before. The other thing that a lot of students say helps them too is being connected to their class's GroupMe. So having neighbors that you can send questions out to get ideas from. So just a lot of different resources available for you. Yeah, Kaylin says she likes the class sessions because she can be more interactive. Absolutely. Between the sessions and the GroupMe, you can do all kinds of interacting, right? All right. Well, we've got some ideas. Especially, again, I'm going to highlight for us, especially as we start learning bone markings and muscles and muscle actions this week in lab, start those flashcards now. Let's start building them. Let's start using them. Let's make the flashcard thing work starting on day one, if you will, in the second half of the semester. So keep up the good work. For those of us that the test was just okay or it was bad, we've got plenty of room to improve. We've got lots of time to improve too. So maybe try some of these things that we weren't using before. Maybe that'll be helpful for us. All right, let's do a little bit of lecture review. I feel like it's been forever since we last did lecture stuff because we had that lab exam. So it's been a minute since we last talked about the structures of the skin. But when we talked about the skin, there were 3 molecules that we talked about. They're listed here. So things called glycolipids, keratin, and melanin. And then we talked about 2 different structures that help us to hold things together. That's the tight junctions and the desmosomes. So here, I just filled this one in for us. When we talk about holding cells together, the 2 things that hold cells together are desmosomes and tight junctions. They're the 2 ways that we connect cells to each other. When we talk about desmosomes, desmosomes are made out of a particular kind of protein. Does anyone happen to remember which protein I used to build desmosomes? Yeah, exactly. So my desmosomes are made with keratin. And that's not a question that we directly put on the slide, but a good thing for us to remember and to review is that desmosomes are my type of junction that are held together or they're strong because of the keratin protein. When you think about the keratin protein, keratin is one of the things I use to protect my skin. So one of the things that protects the skin that makes it tough and resistant to damage is keratin. What other things in our group did we talk about helping to protect the skin? What were some of the other things that we put here? Yeah, so Kira's mentioning melanin. Melanin protects us from UV, absolutely, UV radiation. Hey, could we make a case for glycolipids protecting the skin? Yeah, Elapine is mentioning them. Why could we maybe say that glycolipids protect the skin? Any thoughts on that? Yeah, so it's all about water, right? It's all about making sure we don't get too much water, making sure we don't lose too much water. So glycolipids are one of my things. I'm going to put it in the category below. Helps us to waterproof the skin. In addition to glycolipids, what's the other thing that helps us to not lose too much water or to make sure that not too much water gets inside? There was one other. Yeah, it's those things called the tight junctions, the tight junctions. When we connect our cells together tightly, those junctions prevent there being space for water to sneak in or for water to sneak out. Glycolipids, their name, remember, literally means sugar fat, sugar fat. Glycolipids are one of my things that are made by keratinocytes. One of the things that keratinocytes make are those glycolipids. Their goal being to waterproof the skin. What's the other thing that keratinocytes make? And their name is actually kind of a tip for this one. What's the other thing they make? Yeah, the other thing that keratinocytes make is keratin. So keratinocytes make keratin. That helps your skin to be really tough and resistant to damage. Keratin's good for that. Glycolipids help your skin to be waterproof. So we don't lose too much water, we don't gain too much water. But we also talked about how glycolipids can be a little bit problematic because they block water, which is good from the outside. Why is it bad to block water from the inside? Why is it a problem if we block water that was inside the skin from getting toward the outside? Yeah, so when we talk about blocking the water that's inside, moving toward the cells more toward the outside, what's dissolved in that water is nutrients. So remember that when we talked about glycolipids, or sometimes we called them, our other name for them was lamellar granules. Oh, I spelled that wrong, sorry. When we talk about lamellar granules or glycolipids, we see those in stratum granulosum. And that's where your skin first really becomes waterproof. So water can't get inside, but water also can't go up any further. And dissolved in that water are the nutrients that we need to stay alive. So glycolipids are one of the things that makes my cells in stratum corneum die because they prevent the cells in stratum corneum from getting any nutrients. So glycolipids kill those cells in stratum corneum. The cells in stratum corneum are also completely filled with something. What is it that fills those cells in stratum corneum? Do we remember what they're full of? Yeah, exactly. They are full of keratin. They're full of keratin. So because they're full of keratin and because they don't have access to nutrients, because those nutrients are blocked by the glycolipids, stratum corneum is completely dead. Stratum granulosum is usually mostly dead, or it's dying. It's in the process of dying. Hey, we talked about keratinocytes making keratin. When we talk about melanocytes, what do they make? Melanocytes. Yeah, exactly. Melanocytes make melanin. And we said that melanin is good for blocking UV radiation. What happens if UV radiation gets to your skin cells? What could we possibly have? Yeah, if that UV radiation doesn't get blocked by melanin, we can develop skin cancer. So melanin, its goal is to prevent skin cancer. Yeah, Tian's right. So it damages your DNA. So UV radiation has the ability to go in and actually either slice your DNA so that it's no longer as long as it's supposed to be, or it even has the ability to change the nucleotides that are there. So if it used to be an A, we can flip it to a T or flip it to a C or a G. So it can go through and damage the DNA inside a cell, causing it to start replicating out of control. That's what cancer is. When we go in and we damage our DNA, and I no longer have the sequence that says stop dividing. Cancer is just cells that keep dividing and never stop. UV radiation likes to mess with your DNA. It's particularly bad when we're talking about genes that regulate division or that control mitosis. Yeah, Elapina has listed for us, remember that we have 3 kinds of skin cancer. So we'll review these again really fast. We have things like skin cancer called basal cell carcinoma, squamous cell carcinoma, and melanoma. All of those are skin cancers. Do we happen to remember which of these is the most deadly? Which kind of skin cancer is the most deadly? Yeah, melanoma is particularly deadly. Melanoma is melanoma. Yeah, that is true. Thank you, Dr. Ollis, for stating the obvious. That's what happens when I'm talking and typing. Sometimes it goes wrong. Hey, Kira's like, I'm spot on. That's very true. Okay, melanoma is the most deadly. That is correct. By the way, when I was grading current events, a lot of us picked the article about melanoma in African Americans and how it goes misdiagnosed or undiagnosed, typically until it's much farther along than in people with white or lighter skin tones. If you already did that article, we can't do it again, but it also wasn't necessarily tagged for unit number 1. That would be a great article to do for unit number 2, talking about why melanoma is so often missed or why it is actually a problem in people with darker skin. A lot of times they don't think that it is a problem, but it can be a problem, and it can often be more deadly. Part of that being because it's harder to see a melanoma when your skin has more melanin in general. It's harder for you to notice that you have a melanoma. So if you're interested in learning more about melanoma, there's some good articles for current events that are out there for that one. Melanoma is the most deadly one. Which one do we remember? Which is the least deadly? Basal cell or squamous cell? Who's the least deadly? Yeah, so basal cell carcinoma, that's the least deadly. That one is also the most common. So least deadly, most common kind of skin cancer, basal cell carcinoma. Remember that this one grows slowly, and it also kind of grows in a group, so it's easier to catch all of those cancer cells and get them out. Squamous cell carcinoma, if we were to put them in order from least to most deadly, this is my least deadly, basal cell, because it grows so slowly. Squamous cell grows quicker. It also kind of grows in little individual lines as opposed to groups of cells, so it's harder to catch all the cancer. But melanoma grows the fastest and it travels the farthest. So that's what makes melanoma the most deadly skin cancer. Yeah, and Audrey asked a good question that I want to make sure I clarify on the video for our friends watching. I mentioned current events. Remember that each unit you can do 1 extra credit submission. So everybody needs to do 1 article. You can do 2 articles for each unit. That second article is for extra credit. At this point, we're just doing 1 extra credit per unit. So we've done 1 for unit number 1. Now we can do 1 for unit number 2. We'll do 1 for number 3 and for number 4 as well. So multiple extra credit submissions throughout the semester. Make sure you're on top of that because inevitably at the end of the semester, I get emails from people who never did extra credit ones and they want extra credit. It's like, hey, we've been doing it all semester. So make sure to get those in for unit number 2, your extra credit for that one. All right, one more statement that we have on here, and I purposefully used a big anatomy word that I'm not even for sure certain that we talked about in class. I know it's in our guided lesson though. This big anatomy word that I'm talking about here is amphiphilic. Amphiphilic. Yeah, and he's just like, I learned a new word. Amphiphilic. So the key with this one, even if we have no idea exactly what it means, I know I heard at least one group talking about this. This amphi part is just like amphibian, where they can live on the land and water, right? They live in both places. So when we talk about something being amphiphilic, what we mean is that part of it loves water and part of it loves lipids. Amphiphilic, or loves fats. Or to put it in our chemistry words, like Kira mentioned there, we've got a polar part and we've got a non-polar part. A little bit confused, right? Actually, it's good because part of it's polar and that's going to want to be by water. Part of it's non-polar, which means it's not going to want to be by water. Which of those molecules did we talk about that we said is amphiphilic? Does anybody remember which one we talked about? Amphiphilic? Yeah, it is actually glycolipids. Glycolipids. Partially water-loving, partially water-hating. The water-hating part is the problem part for us because that's what blocks the nutrients. These are sugar fats. Sugar part loves water, fat part not so much. Actually, where I know you've seen this word before, we saw this word when we were talking about the plasma membrane. The plasma membrane. Yeah, when we were talking about the plasma membrane, remember that we talked about phospholipids. Let's do a little bit of art. Phospholipids in the plasma membrane. I know it was like a year ago, right? I agree, forever ago. Okay, remember with the phospholipids that we had 2 parts. The top part of our phospholipid was called the head. The bottom part was called the tail. Which of these parts loves water? The head or the tail? Who loves water? Yeah, the head loves water. So the head was polar. And those tails then were non-polar. Let's move that. The tails were non-polar. So when we talk about the chemistry of a phospholipid, part of it loves water, part of it hates water, and that's why when you look at the plasma membrane, we actually have the bilayer. We have the two structures, right? Because then I've got this space in the middle where there's no water, and these spaces on the outside where there is water. So phospholipids are amphiphilic. Glycolipids are amphiphilic as well. Partially water-loving, partially water-hating. It's that water-hating part, or the part that loves fats, that ends up killing those cells. Before we move on, any questions about these statements? Or give me a thumbs up if we're feeling okay. Questions or thumbs up? Yeah, go ahead, Temiteo.
I'll put my thought together. So for the the tight junction, it says it's made out of plasma from keratinocytes. Will that be considered that it's made out of keratin also?
That's a good clarifying question. When we talk about the tight junctions, they are places where there are some proteins that are embedded in the plasma membrane of keratinocytes that are used to fuse their plasma membranes together. Those proteins that are in the membrane are different than keratin proteins. So keratin proteins are more like cytoskeleton proteins. The kind of proteins that we use to make tight junctions are not keratin. And that's actually kind of an underlined highlight star, an important idea. So let me type it here on our thing. Not made with keratin. Wink, wink, nudge, nudge. That typically this question shows up on the exam. Tight junctions, they are made out of proteins, but it's not keratin proteins. It's those transmembrane proteins that we talked about way back before the midterm exam a year ago, right? When we were talking about places that proteins are in the cell. So the only kind of junction that uses keratin proteins are desmosomes. Desmosomes are built out of keratin proteins. Tight junctions do not have any keratin in them. No keratin in tight junctions.
Okay.
Thank you for that question. That was a good clarifying question.
Plasma from keratinocytes. So I was like, okay, thank you.
Yes. Yeah. So it's got that plasma membrane of the cells that are filled with keratin, but no keratin in it. Yeah.
Okay. Thank you.
All right, let me pull up. Briefly, I'll review with us. Well, here, a couple quick things to highlight what we just kind of talked about. Remember how we said that glycolipids are amphiphilic. So here's my two lipid tails, my two parts that don't like water. Here's my glyco, or my sugar part of it. This is the part that does like water. But these lipid tails, just like in the plasma membrane, these lipid tails make a barrier, which is why nutrients can't get past stratum granulosum. From here up, there are no nutrients. That's part of why these cells are dead. They're also dead because they're completely filled with keratin. So between the glycolipids and the keratin, these guys are dead. There's no nutrients, and there's way too much of that tough, strong protein. We talked about those skin cancers. Remember that your tip-off with melanoma, it's the melanocytes that have become cancerous. When melanocytes get cancerous, they make lots and lots of cells that have color. So we see all the color in a melanoma. And in this picture, the melanoma looks brown, but melanomas really can be all kinds of different colors. They are sometimes blue, they're sometimes kind of red or purple. It just kind of depends on how much melanin is being made. But these kind of lesions, melanoma, when those melanocytes become cancerous, they're always going to be a colored lesion. Basal cell carcinoma growing slowly in a group, like we can see here, and then squamous cell carcinoma, where individual cells grow a little bit faster, making it maybe a little harder to catch. Some of those cells might sneak away. Does anyone happen to remember, we had our fancy anatomy word for when cancer cells spread? What was the name of cancer cells spreading? Change colors here. Yeah, so when we talk about cancer cells spreading from one place to another, the process that they use to do that is called metastasis. Metastasis. So when cells spread from where a cancer started to other places in the body, and with melanoma, here's some of those common places. That's called metastasis. Metastasis is the worst in stage 4 melanoma, where those cancer cells have really spread to other organs, other places in the body. It starts, though, here in stage 3. Remember that in stage 3 melanoma, not only do we have our cancerous lesion on the surface of the skin, so in the epidermis, not only is it into the papillary layer of the dermis and the reticular layer of the dermis, it's actually spread all the way down into the hypodermis, where we have some lymph nodes. And lymph nodes are the place where your immune system has cells chilling out, waiting to catch invaders. But those lymph nodes, like Kira mentioned, they're attached to your lymphatic vessels. And those are kind of like the superhighway that can take you anywhere in the body. If we find cancer cells in the lymph nodes, the oncologist would be pretty nervous, because that means that there's a good chance that those cancer cells have found other places in the body to go to. So again, these are the common places that melanoma in particular likes to spread to. It uses the lymphatic system to get to those places. Remember that the best kind of cancer to have would be a stage 0 cancer. 0 as in it's spread nowhere. So stage 0, it would be confined to the epidermis. Starting in stage 1 then, we're down into that papillary layer of the dermis. Stage 2, we go deeper into the reticular layer, and then we metastasize in 3 and 4. Yeah, exactly. We don't want skin cancer. The unfortunate thing is a very high number of people will develop skin cancer, both from tanning, which there are articles about how bad tanning is in current events, but also just from day-to-day exposure to UV. I'm going to quote the number wrong, most likely, but I want to say it's something like 1 in 5 people will develop some kind of skin cancer. Remember that the most common kind is basal cell carcinoma, the one that grows more slowly, but it is still a skin cancer, and it is still something that you have to treat. So wear your sunscreen, wear your hats, don't do the tanning. Yeah, it is pretty terrible statistics. So take care of your skin. Like our classroom banner said, right? Love the skin you're in. So take care of it. Let's prevent all the skin cancers, right? Yeah, Caitlin says to swim in sweatpants. Might be a little extreme, but you know, if you're wearing sweatpants, you're not getting sunburned. So I don't think it's a bad idea. All right, I think actually now that I'm looking at it, I believe this is the last thing we talked about. Is this correct? I think we did talk a little bit about friction ridges. Okay, so when we were talking about the difference between stage 1 and stage 2 melanoma, it's all about whether we're just in the epidermis, or stage 0 and stage 1. If we're just in the epidermis, or if we've gone down into the dermis layer as well. Remember that the epidermis and the dermis, they meet together with these things called epidermal ridges and dermal papillae. So if you imagine, if you hold up one of your hands and kind of spread out your fingers, so you're like making the number 3 pointing up, and then you take the other hand, spread out those fingers with the number 3 pointing down, and then you kind of stick them together, you'd have your fingers pointing down like we see here, and your fingers pointing up. That's the way that the epidermis and the dermis come together. It's not a flat line. They don't just go straight across, epidermis and the dermis. These dermal papillae, where the dermis reaches up, and these epidermal ridges, where the epidermis is reaching down, these are really great for making sure that your dermis and your epidermis stay connected to each other. So when you're doing all kinds of stuff with your fingers, with your feet, when you're wearing shoes and walking, your skin, your epidermis and dermis is constantly being pulled against each other. By having all of these little ridges and these little papillae, it helps it to stay connected. The way that those things interact with each other ends up forming the technical name being friction ridges, or the normal person name for them being fingerprints. Fingerprints. I believe the very last thing we talked about with this was the fact that everybody's fingerprints, even identical twins, everybody's fingerprints are different from one another, because those fingerprints come from the way that the dermis interacts with the epidermis. No two people have the exact same pattern of the way that their dermis interacts with their epidermis. Hey, so I have kind of a silly story here. One semester when I was teaching, I had this class of students that was kind of fire obsessed. Actually, there was just one student in the class that was fire obsessed because way back at the beginning of the semester when we were learning about organelles, I did this activity with my students where I said, hey, we're all locked in this classroom together for the entire semester and we can't leave. What do we need to survive? And this was my class that the very first thing that somebody in the class said we needed was an incinerator to burn our trash. So I should have known then that we were in trouble because somebody in my class wanted an incinerator. We don't want like trash service. We want to burn that trash. Okay, that's cool. So we get to this lesson in class and my student in the back, he raises his hand and he says, so if I want to burn off my fingerprints, which Kaylin's talking about too, so we got to watch that one. He says, if I want to burn off my fingerprints, what do I have to do for that? So we're relating this to lab here. We talked about the kinds of burns in lab, right? If you wanted to burn off your fingerprints, let's take a step back here. How did we say we made those fingerprints again? Where do fingerprints come from? What gives us that structure? Yeah, so the fingerprints come from the friction ridges, right? And these friction ridges are the way that the epidermis and the dermis interact with each other, right? If I want to change my fingerprint, I'm going to need to change the way that the dermis and the epidermis interact with each other. So in a first-degree burn, what am I burning? Who remembers in a first-degree burn? Yeah, first-degree burn was one layer, right? That's how it gets its name. In a first-degree burn, you just damage the epidermis. If I just damage the epidermis, nothing's happening here with my dermis. It's the same. That's not going to change my fingerprint. In a second-degree burn, remember that the epidermis gets damaged and some of the papillary layer of the dermis might get damaged. The big thing that we talked about with a second-degree burn, how do you know that you have a second-degree burn? What do you see on your skin with a second-degree burn? Yeah, you see those blisters, right? A blister is when the epidermis, these epidermal ridges, separate from the dermal papillae that I see down here. So fluid gets in between. I separate these two layers from each other, but I don't change the shape of the dermal papillae. If I want to change the shape of the dermal papillae, what am I going to have to do? What kind of burn am I going to have to get rid of my fingerprints? Yeah, you're gonna have a 3rd degree burn. Remember from our picture of the lab model, in a 3rd degree burn, you get rid of the dermal papillae. The papillary layer of the dermis is gone. The reticular layer of the dermis is usually damaged. It's usually hurt. But when it grows back, it'll grow back differently. So to answer my fire-obsessed student's question, if I want to get rid of my fingerprints, or if I want to change them, I'm going to have to do a 3rd degree burn. I'm happy to see in the chat that Kaylin says that would not be worth it. 3rd degree burn to change your fingerprints, yeah, probably not worth it. Remember though, 3rd degree burn, when it happens, doesn't hurt because we fried all the nerves. But when we start regrowing new fingerprints, that is going to be very painful. Yeah, exactly. You would pay later. So your fingerprints, again, they come from the way that the dermis and the epidermis interact with each other. Friction ridges or fingerprints, in easy person words. The other thing for us to know about the dermis, besides the fact that it helps us make our fingerprints, the other thing for us to know is that the dermis layer is what we call highly vascularized. Highly vascularized. Do we remember what that word vascularized means? Anybody remember what vascularized means? Yeah, exactly. So this vascularized word is the same root as we see in the cardiovascular system. It's all about blood vessels. Blood vessels. So when I talk about the dermis layer of the skin, notice how I've got some blood vessels that are up here in the papillary layer. I've got much bigger blood vessels that are down here at the bottom of the reticular layer. And then we might even have some blood vessels down here in the hypodermis layer of the skin. But primarily we're focusing here on those ones in the dermis. Hey, not a trick question. When we were talking about the epidermis, does the epidermis have blood vessels inside of it? Did we talk about blood vessels in the epidermis? Yeah, we did not. The epidermis, remember, this is when we were talking about those glycolipids, right? The epidermis gets all of its blood, so all of its nutrients and oxygen and stuff, from the dermis. The epidermis is what we call avascular. Avascular, meaning it has no blood supply. This is why, by the way, if you get a paper cut and that paper cut doesn't bleed, it probably means we just damaged the epidermis because there's no blood vessels to bleed in there. When we get down into parts of the dermis where we've got all the blood vessels, highly vascularized, that's going to be a paper cut that bleeds and probably that hurts worse, right? But the epidermis layer, avascular, no blood vessels. The dermis layer, highly vascularized, lots of blood vessels. And one of the things that those blood vessels in the dermis help us to do is thermoregulation. So perhaps one of the biggest reasons we have so many blood vessels in the skin is to help us out with our body heat. For us to have a discussion about thermoregulation, we need to talk in general about the way that your body keeps yourself stable, or the way the body can do things. These things that we're getting ready to talk about are called homeostasis loops, or homeostasis. When you're looking at this picture, at this balanced state that I see right here, when you think about balance, that's kind of what that word homeostasis means. Homeostasis. So your body has a set of conditions that are things that it likes to normally maintain. So we're always roughly the same temperature. We always have roughly the same amount of glucose in our bloodstream, roughly the same amount of salt. So there are particular things that we keep in balance or we have what we call a set point where we want our body to be at. But we live in Texas, for example. We're going to do a thermoregulation one. We live in Texas, so in about, what do we think, 1 month or less, we're going to start having that Texas heat, right? So it's going to start heating up. A stimulus like the Texas heat outside, it's something that can impact your body's balance, impact homeostasis. So we walk outside here, we'll be more generous. We'll say in July. We'll hope that July is when the heat comes. We walk outside in July. There's a stimulus of it being 102, feels like 115. Stimulus is that heat outside. Your body starts to heat up. We start to go away from our balance state and our body starts to heat up. Our body detects that we're out of balance using things called a receptor. So a receptor is what's constantly monitoring your body, checking to make sure that we're in balance. As long as we're in balance, the receptor is really bored and it has nothing really to do. But the moment it detects that we are out of balance, the receptor sends that information up to the control center. Typically, the control center is your brain. Sometimes it can be your spinal cord. Sometimes it's a part of the endocrine system, the hormone system. So we send our message that we're out of balance to the control center. The control center acts on what are called effectors. These are things that when they do their job, it helps us to get back to normal. So the effector is going to help us return to balance. This is the way overall that homeostasis works. So in your body, we know what we want. We have receptors that are listening for it to not be correct. We have control centers that can fix it when it's not correct, or that know how to fix it. Let me rephrase that. Control centers know how to fix it. Effectors actually fix it for us. So in the context of body temperature, because that's what we're talking about with the skin. In the context of body temperature, we're talking about the process of thermoregulation. As our bulletin board said, today we're going to talk about why you're so cool. So thermoregulation, what makes you cool or what makes you in balance. When we talk about balance, or when we talk about the set point, the normal point that we want to be at, what do we say is the normal temperature set point? What's about normal for humans? Yeah, so we typically say 98.6 degrees Fahrenheit. Do I have any micro friends in here right now? What's the other number for that? Do we know? Yeah, so the other number that we use to describe 98.6 is 37 degrees Celsius. Yep. I had read about this. I don't remember exactly where. They're actually considering revising what they say is normal body temperature. Pretty much no one is 98.6. I don't know about you all, but I typically run in the 97s. So if I'm 98, 99, that's a bigger deal for me than you know, if I'm a 98.6. So there was some chatter. I'm not sure if they'll ever actually change it because medicine is slow to follow the science, but most people aren't 98.6. Most people are a lot lower than that. That's a good segue though. When we talk about these set points, when we talk about what balance is not typically just one number. Like your body is not going to freak out if you're at 98.4. And it's not going to freak out if you're at 99. There's a set range that's about normal for your body. So we use the terminology, you'll see this in your notes, of set point, called the set point. It's actually more like a range of values, a range of acceptable values. Now, when we go outside in the Texas heat, we have the stimulus of the Texas heat, we are definitely going to go higher than 99. If it's really hot outside, we're gonna go up. So our body temperature is rising outside of our normal range. we have receptors that would detect that. We kind of check your temperature in two places. The first place we check it is your skin, because that gives us an idea of what it feels like outside as well as inside. The second place we check it is actually in your brain, though. So your brain is constantly checking the temperature of your blood. Your blood runs warmer than your general body temperature, but if your blood gets really too hot, and we can detect it in the brain, that's when these receptors would get activated. By the way, when your body temperature is too high, we have a special name for it. It literally means too much heat. Too much heat. Yeah, too much heat is hyperthermia. Just like hypertonic was too much concentration. So if my body's in the state of hyperthermia, my receptors in the skin and my receptors in the brain would detect that. They send that information up to a part of the brain called the thermoregulatory center. The thermoregulatory center is in charge of regulating your temperature. Your body gets the message. The message says, we have hyperthermia. We are too hot. Body takes that message and it talks to two effectors. Let me fill in my little box here. It's going to talk to two effectors. Does anyone remember what the effectors are when our body is too hot? What are we going to do when we get too hot? Yeah, so one of the things we're going to activate are going to be those eccrine glands. Remember from lab that eccrine glands make the watery sweat that makes you cool. So when you're too hot, the first thing I'm going to do, turn on those sweat glands. Dump out some of that hot water from the body. The other thing I'm going to do is I'm going to activate the blood vessels in the skin. My goal is to get as much blood as possible to the skin because that blood can radiate off heat. So when we talk about the blood vessels getting activated when it's hot, do I do vasodilation or vasoconstriction? Which one means that we're getting bigger? Yeah, vasodilation. Vasodilation. That means we're making our blood vessels bigger. When you're too hot, we send more blood to your skin. That's why you maybe look flushed after exercising. Your skin feels hot because we're sending all of that heat to the skin where we're going to get rid of our sweat, where we're going to get rid of some of that heat in our blood and get us back to normal. So when you're in a state of hyperthermia, the effectors that we activate are your watery sweat glands and your blood vessels that do vasodilation. They're gonna get bigger. Being too hot is something we're used to in Texas. What we're not used to in Texas until this year, right? Until 3 weeks ago, is extreme cold. What is it called when your body temperature is too low? We're used to hyperthermia. Yeah, we are not used to hypothermia in Texas. Maybe we're going to get used to it, right? I hope not. Let's not have another thing like that happen again. Can we all agree? Yeah, we should not be having hypothermia in our house. I agree with that statement. Okay, so hypothermia, ERCOT lost power to the entire state of Texas, and we're all freezing. Our body temperature is falling. Again, my temperature-sensitive cells that I find in the skin and the brain, the same ones that up here detected that I was too hot, now down here they're detecting that I'm too cold. They're going to send that new message up to the control center. The control center gets the message this time that we're too cold. The control center knows who can fix it. So the control center is going to send a message again to our effectors. What are the effectors that you use when you've got hypothermia? Yeah, so the first one we're going to use is skeletal muscle. One of the functions of skeletal muscle is to generate heat. Generate heat. In particular, the way that we're going to generate that heat is by shivering, right? So you start to shake, you start to shiver. That generates heat. We are also, in addition to trying to generate heat, we're also going to talk to the blood vessels and tell them to stop losing heat. So when we have hypothermia, yeah, now my blood vessels are going to do what's called vasoconstriction. Vasoconstriction, where they get smaller. We're going to send less blood toward the skin. By sending less blood toward the skin, we're not going to lose as much heat. It's not going to radiate off the body as much. So we're keeping our blood away from the surface of the body where it's really cold. We're also shivering the body, contracting that muscle to create more heat. These things together help us get back to balance. Hey, you will see this on the homework assignment, and you will also see on the exam. We definitely need to pay attention to the words vasodilation and vasoconstriction. It would not help me if I'm feeling really hot to do vasoconstriction, because that's going to keep that heat inside of me. Just like if it's really cold, it wouldn't help me to do vasodilation, to lose all my heat to the surface of the body. Please make sure to watch those blood vessel words, dilation and constriction, as you're working on the homework assignment, as you get to the exam. Watch those words too, hyperthermia and hypothermia, because I do the opposite thing if I'm too hot versus if I'm too cold. Thermoregulation is an example of something that we call a negative feedback loop. Negative feedback loop. What that means is my stimulus is taking me away from normal. I'm getting too hot or I'm getting too cold. And my body's job is to do the opposite of that. I want to get back to normal. So in a negative feedback loop, something happens. Either it's really cold or it's really hot. My body is going to do the opposite of what's happening. Negative feedback loops, we want to get back to normal ASAP, right away. Most of the things in your body are regulated using a negative feedback loop. In other words, you've got a balance that you always want to stay really close to. Your body's going to fight for it to keep you there at balance. There are some things, I'll come back to that. There are some things, though, that our body uses what's called a positive feedback loop. A positive feedback loop. In a positive feedback loop, we get a stimulus. So something happens. In this case, we're looking at the process of blood clotting. So say we got a cut. We talked about those paper cuts, right? Say we got a deep enough paper cut that we cut one of the blood vessels in our skin. So when you cut one of those blood vessels in your skin, what's going to happen is some platelets are going to get damaged when that blood vessel gets damaged. When platelets get damaged, they spit out some chemicals that help them to form a clot. Clots are made out of proteins. When our platelets spit out these chemicals, we build proteins right away there in the bloodstream. Well, when a couple of platelets spit out their chemicals, not only does that start to build a clot, build those proteins, it also calls over other platelets. And those other platelets stop the chemicals too, because, oh my gosh, we've got a problem. So they come over, they spit out their chemicals. We make more of a clot in that blood vessel wall, but also we're spitting out chemicals. Those chemicals recruit more platelets. So more platelets come over, spit out more chemicals. This positive feedback loop, this loop of I spit out my chemicals, which calls over more platelets, which spit out their chemicals, which calls over more platelets. This is an example of a positive feedback loop. When you think about a positive feedback loop, consider this more like maybe we're creating a new normal, or in some regards, maybe even almost like a new set point. Normal situation, we don't want our blood clotting. That's bad news. When we have a blood clot in the brain, the blood vessels of the brain, that's a stroke. So we don't want blood clots normally. But if your blood vessel is torn, if that's my stimulus, I want a new normal. My new normal is blood clotting. So I'm going to keep calling over platelets and spitting out those proteins until I've created a clot that completely closes off this blood vessel wall. At that point, my positive feedback loop has done its job, and I'm done. I'm done clotting. I'm going to go back to my original set point. But when we think about the positive feedback loop, to put it in feedback loop structure terms, we would say that our effectors, which are what make things happen, they do the same thing as the stimulus. So in a positive feedback loop, a couple of my platelets exploded. That's the stimulus. That causes more platelets to come over, my effectors. They explode too, which causes more platelets to come over, and they explode too. And it goes on and on and on until we're done. So positive feedback loops, not nearly as common in the body. Blood clotting is a good example. Do we remember what's the other example? Did we talk about the other example of positive feedback loops? One that's pretty near and dear to my heart recently. Oh, maybe I didn't put it in the lesson. Okay, well, the other example of a positive feedback loop is the process of childbirth. Process of childbirth. When a woman goes into labor, we contract the uterus, which pushes the baby. The baby pushes on the cervix, which sends a message to the brain to contract the uterus. So the uterus contracts, pushes on the baby, message goes up to the brain. It goes and goes and goes. We set up a new set point, which is the uterus contracting, until we have accomplished the purpose of birthing a child. Then that positive feedback loop is done. So it's not normal for the uterus to be contracting, except when a woman is in childbirth. When the baby is big enough, when it's low enough on the cervix, that's how the process of labor starts. So the stimulus is the child descending, which starts its own positive feedback loop for the process of childbirth. So another example of a positive feedback loop, again, not nearly as common as negative feedback loops. So in a positive feedback loop, whatever your stimulus was, effectors keep doing it. In a negative feedback loop, whatever my stimulus was, my effectors do the opposite. They want to get us back to our original set point. So if you get hot, your body's going to cool you off. If you get cold, your body's going to heat you back up. Remember that for both of these processes, we do use blood vessels. We use blood vessels to make you warmer and to make you cooler, but we do different things depending on whether we're making you warmer or cooler. I've talked a lot. I need to pause and give you a chance to ask any questions that you have about the integumentary system, about the skin. Or shoot me an emoji. How are we feeling? I'll give us a little dance party. And give us a penguin. Penguins don't shiver. Actually, they probably do. I don't know a lot about penguin physiology. I should probably read into that. Audrey's brain is on fire. So Kaylin was asking about the difference between positive and negative feedback loops, asking if the goal is the same. The goal is actually opposite. So in a negative feedback loop, we want to get back to normal as quickly as possible. In a positive feedback loop, we actually want to not be normal for a while. So when we're looking at our blood clotting example, the goal of blood clotting is for your blood to keep clotting for a while. We want platelets to call over other platelets, to explode and call over other platelets. We actually want the blood to be clotting. If we didn't have this tear in our blood vessel wall, normally we would not want there to be blood clotting. That's bad news. So in a positive feedback loop, we create a new normal that we're going to do for a while. Eventually, that new normal will end, but the positive feedback loop itself is what we see going on right here. So the fact that some platelets call over other platelets, call over some platelets, this is the positive feedback loop. So our new normal is blood clots. Normally, if we think about kind of a more negative feedback approach, would be that we don't clot. We make sure we don't clot. That's normal for you, so that that blood can get everywhere it needs to go. Does that help? Okay, perfect. All right, well, I've got about 20 minutes left. In that time, I want to start talking with you all about the skeletal system. Let's chat briefly about our schedule for this week and how I think you should be spending your time. If possible, between now and tomorrow's class, it would be really great for you to work your way through lesson number 8, so through the skeletal system. If possible, taking a peek at some of those resources for the skeletal system disorders would be helpful too. Full disclosure that disorders assignment is going to take a good chunk of time. So please don't put that off until the very end of spring break. Please try to start working on it tomorrow so that you have an idea of what the assignment looks like. We will review on Friday. I'm happy to review some of the disorder stuff with you, although I suspect we're probably going to want to be reviewing some central dogma stuff on Friday. But if you can work your way through lesson number 8 for tomorrow, that'll put you in good shape to know what kinds of questions you have about that, and especially by Friday to know what kinds of questions we have for the skeletal system disorders as well. So let me pull up, let's see, let me pull up some pictures of our different types of tissues. Let's do some compare and contrast together here. Normally I would give this to you in groups, so alas, I'll have to come up with a new activity for tomorrow. But I think this is a good way for us to remind ourselves of what's going on with our tissues. When I am looking at my types of tissues here, yeah, so the first thing we need to do is we need to identify these. This should be a breeze after the midterm, right? So my top one up here, yeah, right, we're saying, oh yeah, this is easy. My top one here at the very top, I'm seeing compact bone and spongy bone. Number 1, here, let's label it. Number 1. Number 2, number 3. Start with number 1. What kind of tissue is number 1? Now that they have numbers. Should be easier for all of us. Yeah, so number 1, that is spongy bone. When we're looking at the spongy bone, we can tell because remember, we've got the pink bone tissue and then the bone marrow that's mixed in between it. So number 1 is spongy bone. For number 2, I'm seeing a couple of votes for hyaline. We thumbs up on the hyaline for number 2. I'm seeing lots of votes for hyaline. Hyaline cartilage. Yep. Okay. And then for number 3, what kind of tissue are we seeing for number 3? Exactly. Number 3 is that compact bone. Compact bone. Look at that. I'm just saying, like 2-3 weeks ago, if I popped these pictures up, they would have been more scary, right? So regardless of how you feel like the midterm exam went for you, we looked at these pictures and we feel relatively confident on them. So look at that. We've made some progress, even though it may not have been the progress that we wanted, or it may have taken a lot longer than we wanted it to. Props to us, right? We've made progress. All right, let's go through and we are going to figure out which of these types of tissue that we see over here match up with our statements. So my first statement on here is asking about which ones are a type of connective tissue. Which of these are a type of connective tissue? So a couple of us are voting number 2. That is correct. And then a couple of us are voting all of them, which is actually the most correct. Yep. So when we talk about each of these, to fully identify them, we would add connective tissue after their name. So spongy bone, connective tissue. Hyaline cartilage, connective tissue. Compact bone, connective tissue. So all 3 of these are a type of connective tissue. When we talk about the fetal skeleton, what was the type of tissue that you learned as being found in the fetal skeleton? Who builds the fetal skeleton? Yeah, exactly. Hyaline. Hyaline cartilage connective tissue builds the fetal skeleton. As we'll talk about next time, we turn that fetal skeleton into bone tissue using a special process. Typically, when we're talking about bone tissue, which kind of tissue lives on the outside? What's the kind of tissue that's on the outside of your bones? Yeah, exactly. On the outside of the bones, that's the compact bone. When we talk about the kind that's got bone marrow, we can actually see the bone marrow in the picture, right? Yeah, the bone marrow found on our spongy bone. Absolutely. Okay, let's look at some other statements. Which of our types of tissue have osteocytes? Osteocytes. Remember, osteocytes, their name technically means bone cells. Bone cells. Yeah, so my 2 types of bone tissue, which we had the spongy bone and we had the compact bone, those are my 2 types that have osteocytes. Those are the black spots on the bottom picture, right? And then there's some light pink spots that we see on our spongy bone as well. Hey, what's the deal with this word chondrocyte? Does anyone remember what chondro means? Chondro? Yeah, chondro is cartilage. Chondrocytes are cartilage cells. So my 1 type of cartilage that we had in our picture here was that hyaline cartilage. Hyaline cartilage. So that's going to have chondrocytes, all of those deer tracks in the snow. Those are my chondrocytes. Who's got trabeculae? What kind of tissue has trabeculae? Trabeculae. Yeah, exactly. Trabeculae, remember I told you that word means little beams, or the little fingers is the way I like to think about it, of bone tissue. That's the solid pink stuff that mixes all over the face, called trabeculae. Who's got osteons? Which kind of tissue has those osteons? Yeah, exactly. Osteons, I'm going to circle one here. Osteons are the central canal, that dark spot, and then those concentric lamellae, those lines of cells that we find around it. Last question here asks about extracellular matrix. Help me out with this extracellular word. What does extracellular mean? Yeah, exactly. Extracellular, outside the cell. Okay, so extracellular matrix basically just means stuff around the cells. Which of my types of tissue up here have stuff on the outside of the cells? Yeah, exactly. We're saying all of them, right? All of them do. Totally correct. All of my types of these tissues that we're looking at, they are all connective tissues, which means they all have extracellular matrix. Now, the extracellular matrix is not the same when we're comparing these types of tissues. So let me see. I can build a table like you have in your notes. I'll kind of put some of those ideas on our picture here. Before I compare extracellular matrices, help me out here. On the left, which kind of tissue are we seeing again? We're just going to be like total whizzes at identifying our tissue, right? Yep, we got that hyaline, cartilage, connective tissue. Hyaline, cartilage, connective tissue. And on the right, we are looking at, exactly, compact bone, connective tissue. Awesome. Okay, so we already kind of said this because it was on our last slide here. When we talk about our cartilage, connective tissue, remember that those cells are called chondrocytes. And anytime you see chondro, we are always thinking cartilage. Chondro always means cartilage. Here, let's add that note. Chondro equals cartilage. This is an underline highlight star idea. We must know. Chondro always means cartilage. So a chondrocyte is a cartilage cell. When we talk about the extracellular matrix of hyaline cartilage, we're talking about a compound called chondroitin sulfate. Chondroitin sulfate. Emphasis being on chondro. You can see chondro in that. When we talk about bone connective tissue, we don't have chondrocytes. What were those cells called again? What kind of cells were in compact bone? Yeah, exactly. Compact bone and spongy bone both have osteocytes. Osteocytes. Osteo always equals bone. Osteo always equals bone. Hey, fun fact. In Oklahoma City, so up 35, they have a place called the Museum of Osteology. What do you think the Museum of Osteology has? Yeah, exactly. Many, many types of bones. It's actually a museum full of skeletons of all kinds of different animals. So they've got a giraffe skeleton, they've got a whale skeleton hanging from the ceiling, they've got a hippo, they've got like bulldogs next to chihuahuas. It's just the coolest bone thing ever. So your nerd teacher is recommending for you, if you ever happen to be in Oklahoma City, check out the Museum of Osteology. All kinds of different skeletons, very, very cool. So your nerd teacher there, moment. Museum of Osteology, where we would see a lot of osteocytes, bone cells. When we talk about bone tissue, my extracellular matrix is no longer chondroitin sulfate, because chondro was cartilage. Now we're talking about calcium phosphate, exactly. Yep, calcium phosphate. Emphasis being on the calcium. Calcium makes your bone tissue really hard. So when we look at our picture of the compact bone, all that beige stuff or white stuff that you see, that's the calcium. Mixed in it though, compact bone or bone tissue in general also has a lot of collagen. Hey, so collagen is a protein. Like we had keratin helping the skin to be tough, collagen is in bone tissue, helping bone tissue to be tough. And the best analogy I can give you for the two parts of bone extracellular matrix is think about if they're building a road and they lay down that metal stuff first. That metal stuff, I believe, is called rebar. So you see all those metal stuff, and then they pour the concrete on top of it. When we're thinking about our bone tissue, collagen is like that rebar. It's the stuff that makes the road resistant to warping, to changing shape, that kind of stuff. Collagen makes your bones resistant to breaking. Calcium phosphate is like the cement that makes them really hard. So calcium phosphate and collagen, this is the extracellular matrix of bone tissue. Especially the calcium phosphate, that makes your bone tissue really strong, really hard. Chondroitin sulfate is a lot more squishy. So the fetal skeleton is a lot squishier than the adult skeleton. A lot of that because of this chondroitin sulfate, this squishy stuff. There is some collagen proteins mixed in out here. That's why some areas are maybe a little bit darker pink. They have a little more collagen, but not nearly as much collagen as we see in bone connective tissue. Somebody mentioned this before too a while back in the chat, and it's an important reminder for us. Whether we're talking about chondrocytes or whether we're talking about osteocytes, the name of their homes is still the same. What's the name of the homes of cartilage cells or bone cells? Exactly. Homes for these cells. In both cases, those homes are called lacuna. Any of my kinds of bone tissue, so compact bone and spongy bone, and my cartilage tissue, we always see these lacuna, these homes for the bone cells. As a connection point here to think about it, the reason I have to have lacuna, I have to have these homes, is because of my extracellular matrix. I need a place in this tissue that's just specific to the cells. They need a home where there's not chondroitin sulfate squeezing right next to them. Or they need a home where there's not calcium phosphate and collagen. That's what the lacuna are, the homes for these cells. We already kind of made the comparisons between compact bone and spongy bone, but just as a review, remember that spongy bone is called spongy because it's got open spaces, so it's like a sponge. These are my trabeculae, my little fingers of bone. You can see those little osteocytes inside their lacuna. Those lacuna aren't arranged in those pretty lines like we saw, like we see over here in compact bone, so we don't see the lamellae, the lines of the bone cells, but it's still bone cells that still live in homes over here. And remember that this central canal with those lamellae that make lines around it, all of those things together are what we call osteons. And we only see osteons in compact bone. That's the only one that has these arrangements. Because spongy bone doesn't have those blood vessels in the central canal, so they're not going to have osteocytes. You've got this cartoon. Can someone help me out? What page of the lesson number 8 packet do you have this picture of bone tissue? Okay, I'm seeing a note about page number 8. Awesome. Okay, so here's what we'll end with today. Just to show you, when we talk about a typical bone, this bone here like the femur, remember that we said on our first set of slides for this that the outside of the bone is where I find compact bone arranged in those osteons, so the central canal with the concentric lamellae around it. We find those in the outside of our bone tissue. The spongy bone with those trabeculae, those little beams, that's found in the middle of the bone in that open area called the medullary cavity. So we find it lining there really close. We also find spongy bone in the two epiphyses at the two ends of the bone. So lots of spongy bone in those places, a little bit of spongy bone lining the medullary cavity, all of the compact bone on the outside. This compact bone makes the bone really strong. The spongy bone makes your bone a little bit lighter, like makes it physically weigh less, so that it's easier for you to move your femur. But we've got to have this strong stuff here on the outside to give a flat surface for muscle attachment, to make that bone really sturdy. That's the job of the compact bone. I am going to stop there for today. In tomorrow's class, we're going to wrap up the rest of lesson number 8 about those particular bone cells, about hormones and exercise and braces, and we'll try to take a little time at the end as well to talk about disorders. Before I close out class today, do we have any last-minute questions about the skin or the skeletal system? Kira's good. I don't think I've actually sent you all an emoji penguin yet. I drew you one for once, but here's my emoji penguin for you. All right, well, I will go ahead and wrap up the recording then. I'll stick around for any last minute questions. But again, tomorrow we'll wrap up lesson number 8, touch a little bit on those disorders, and that will be the end of new content for unit number 2. So have a great afternoon. I hope to see you again tomorrow.